Hello everyone, my name's Navya and today I am going to be concluding Physics 2 with Lab 5, Magnetic Braking with Faraday's Law. So a quick introduction about this lab. The purpose of this lab is to explore the concept of Faraday's Law of magnetic induction through a physical setup and a computational model that will be done through GlowScript. And a few fundamental principles that we will apply in this lab include Faraday's law and Lenz's law, the Biot-Savart law, Newton's law, and here's a quick preview of the main results, in which the experimental time is through the physical setup, which we obtain 1.558 seconds, and the computational time 1.01 seconds. So what are some of the key concepts that we're going to be covering in this lab? So number one, Faraday and Lenz's law. When a bar magnet moves near a coil, a changing magnetic flux produces an EMF, which is part of Faraday's law. Now, nature abhors this change in flux. Therefore, in order to oppose the change in magnetic flux, the induced current creates a non-Coulombic electric field to oppose the flux. And of course, the Biot-Savart law from our previous lab. So to summarize the Biot-Savart law, it simply quantifies the magnitude and direction of the magnetic field, followed by Newton's law, specifically the third law, in which for every action there's an opposite and equal reaction. So here's a quick summary of the physical setup. So as you can see, the system is the bar magnet and the surrounding is everything else, including this aluminum foil that you can see in this picture. So here are the initial conditions of the physical setup include air resistance is negligible, the bar magnet is thought of as a magnetic dipole, and the only forces at work here are gravity and magnetism. So how is this lab set up? So first, the north pole of the bar magnet is marked using the magnetometer app that we used in lab 3. Once we've done that, we drop the bar magnet through this aluminum foil and we catch it, and upon contact we record the time, and this experiment is repeated 5 times, as you can see in the preview of this slide, in which we conducted 5 trials and recorded the time using a stopwatch in seconds, and from there we took the average, in which we got 1.558 seconds. So next up, the computational model. So using the starter code that was provided to us, I set up the initial conditions, as you can see in the code. If you want a closer look, I suggest checking out the link in the description below. And from that code, we obtained this graph in which velocity of the bar magnet was recorded in time recorded in seconds, in which we got the time as 1.01 seconds. So what is the simulation? So what did we interpret from this simulation? So these are a list of questions that the lab report covered. Number one, the intent, in which color corresponds to the clockwise current and which one the counterclockwise, and how can I tell? So red is counterclockwise, whereas blue is clockwise according to Lenz's law. Number two, what happens to the dynamics of the system when you flip the magnet around? The magnet would still continue the downward motion, but the direction of the current would be reversed. And number three, how does the total time of the tube of your real-world system compare to that of the computational system? Well, the computational model would have a slightly higher degree of accuracy than the physical experiment, as it accounts for human errors. And lastly, what does the shape of the velocity versus time flow tell us about the forces? So in the initial part of the experiment, the gravitational force is more than the magnetic force when it enters the tube, and eventually both forces will become equal when the bar magnet is inside the tube. So here are some of the possible errors that could have interfered with the accuracy of our experiment, followed by the discussion questions. Thank you so much for being with me through this entire semester, and I thank you.